Welcome to LessonBC Media. Today we're diving into the fascinating world of charges and electrostatics. Have you ever noticed how a balloon can stick to a wall after you rub it on your hair, or how tiny pieces of paper leap toward a comb that's just been brushed through your hair? These everyday wonders are all thanks to electric charge, one of the most fundamental properties of matter. In this lesson, we'll uncover what electric charge is, explore its types, and see how these invisible forces shape the world around us. Get ready to discover the science behind these magical effects as we begin our journey into electrostatics. Start by understanding what electric charge really means. Electric charge is a property of matter that causes it to experience a force when placed in an electric or magnetic field. There are two types of charges, positive and negative. Like charges repel each other while opposite charges attract. This is why a charged balloon can stick to a wall or why a comb can pick up small pieces of paper. Objects become charged by gaining or losing electrons, and this transfer can happen through friction, contact, or induction. These simple interactions are at the heart of many phenomena we see every day. Now let's look at how different materials interact with electric charge. Conductors, like metals, allow charges to move freely, while insulators such as rubber or glass keep charges in place. This difference explains why some objects easily become charged and others do not. When charged objects interact, they exert forces on each other, described by Coulomb's law. This law tells us how strong the force is between two charges, depending on their size and distance apart. We also introduce the concept of the electric field, which is the region around a charged object where its force can be felt. Understanding these ideas helps us see how invisible electric forces shape our everyday experiences.
Have you ever wondered about the science behind that little zap of static electricity you get from a doorknob? Or, why your socks seem to have a magnetic attraction in the laundry? Well, it's not just some random annoyance. It's actually a peek into one of the most fundamental forces in the entire universe. And today, we're going to pull back the curtain on that force: electrostatics. So, what is this invisible force that's holding pretty much everything together? It's not magic, it is pure physics. And I promise, by the end of this, you're going to have a really solid grasp of the basic rules that run the whole show. All right, to get to the bottom of this, we have to start small. I mean, really small. We have to start with this single, fundamental building block of all things electric: the electric charge. Just think of charge as a basic property of matter, kind of like mass. Every atom out there has positive protons and negative electrons. Now, most of the time, they're perfectly balanced, but when you get an imbalance, a few too many electrons or not quite enough, that's when an object becomes charged, and that's when all the interesting stuff starts to happen. And we measure how much charge there is in a unit called the Coulomb. So how do these charges actually interact with each other? Well, it all comes down to one simple, beautiful rule you've definitely heard before: opposites attract and like charges repel. That's it. This one single idea is the engine behind everything else we're about to talk about.
Now, charge has two rules that it absolutely never breaks. First, it's conserved. That means you can't just create or destroy charge out of thin air. You can only move it from one place to another. Second, it's quantized. This is a cool one. Think about it like money. You can't have half a penny, right? Well, charge is the same. It only comes in these tiny, indivisible little packets, the charge of one single electron. So any charge you ever find is just a whole number of those little packets.
Okay, so we know charges either attract or repel. But that begs the question: how strongly do they attract or repel? For that, we need our first major tool, an amazing equation called Coulomb's law. This formula right here tells us the exact force between any two charges. But the really important part to look at is the r squared on the bottom. This is what's called an inverse square law. It means if you double the distance between two charges, the force doesn't just get cut in half. No, it drops by a factor of 4. This force gets weaker really fast as things get farther apart.
But hang on, this brings up a really fascinating question. How does a positive charge way over here know that a negative charge is way over there? How do they feel this force across what looks like totally empty space?
Well, the answer is one of the most powerful and beautiful concepts in all of physics: the electric field. It turns out that space isn't empty at all. It's filled with this invisible field of influence. You see, every single charge creates an electric field that radiates outward and fills all the space around it. The best way to think about it is like an invisible map of force. If you drop another charge anywhere on this map, the field at that exact spot tells it which direction to go and exactly how hard it should get pushed. It's the force per unit of charge. So how in the world do you visualize an invisible map? Well, we draw what we call lines of force. A great analogy is to think of them as currents in a river. The arrow tells you which way a positive charge would get swept along, and how close the lines are tells you how strong the current is. Where the lines are all bunched up, the field is strong.
And the rule for drawing these things is super simple. The field lines always point away from positive charges, like they're flowing out, and they always point toward negative charges, like they're flowing in. Simple as that.
Okay, now trying to calculate these fields for really complex shapes can get, well, mathematically it gets really hard really fast. But physics has given us this incredibly elegant and powerful shortcut for certain situations. It's called Gauss's law.
Seriously, just imagine trying to add up the tiny little field from every single charge on the surface of a metal sphere. I mean, it would be a total mathematical nightmare. Gauss's law lets us just completely sidestep all of that complexity by looking at the problem in a totally different way. And that new way involves an idea called electric flux. Now, don't let the name scare you. It's easy. Just picture those electric field lines as rain. Flux is just a measure of how much rain is passing or piercing through an imaginary window frame you're holding up. That's it. And here is the law itself. It says something just incredibly profound. It says that the total flow of the electric field piercing out of any closed box you can imagine depends only on the total amount of charge you've trapped inside that box. It's a direct link between what's on the inside and what's happening on the surface.
So, this is the aha moment right here. It doesn't matter if we draw a tiny little surface like S1, a bigger one like S2, or some crazy lumpy shape like S3, as long as they all have the same charge Q trapped inside them, the total number of field lines piercing through each surface, the total flux, is exactly, precisely the same. That is the incredible power of Gauss's law. Okay, we've got the theory down. So how does all of this actually connect to the real world, to real materials? Let's bring all these ideas together and talk about conductors, insulators, and energy.
So materials pretty much fall into two camps. You've got conductors, like a copper wire, where electrons can move around freely, almost like water. Then you have insulators, like plastic, where the electrons are locked tightly to their atoms. This one difference leads to a huge consequence. Since the charges in a conductor can move, they always rearrange themselves to perfectly cancel out any electric field. So the static electric field inside a conductor is always zero. Always. Now let's talk about energy. Electric potential, which you and I just call voltage, is basically the potential energy per chunk of charge. A fantastic way to think about it is like electric pressure. Just like water naturally flows from high pressure to low pressure, positive charges get pushed from a high voltage to a low voltage.
And this leads to a really interesting, kind of surprising result. We just said the electric field inside a conductor is zero, right? Well, that means it takes no work, no energy to move a charge from one spot to another inside it. And that means the electric potential, the voltage, is constant everywhere on and inside a conductor. The electric pressure is totally uniform.
So let's just wrap it all up. We started with that simple rule, opposites attract. From there, we learned that charges create electric fields all around them. We found an incredible shortcut, Gauss's law, to understand those fields. And finally, we saw how all this plays out with real materials like conductors. That's a pretty powerful toolkit for understanding the world of electrostatics. And that brings us to one last big thought. Gauss's law isn't just some clever trick for physics problems. It's actually one of what are called Maxwell's four equations, the fundamental rules that govern all of electricity, all of magnetism, and even light itself. These are the laws that built our modern world. And to think, it all started with just a